let's jump into chemistry. So I know not everyone has had a chemistry class. It's not a prereq for this class, and that's fine. The goal of this chapter is to make sure we're kind of all on the same page when it comes to chemistry. If you took general biology 1, you've seen this material before. Most of it's a review. If you're taking general biology right now concurrently, you might be seeing it kind of at the same time. I'm not sure how it's lining up. But my goal for this is really just to make sure everyone is on the same page. We're talking about chemistry because that's kind of the basis of life. Chemistry is the basis of life. So I'm only going to focus on the aspects of chemistry that apply to human anatomy and physiology. We're not going to go into really any extreme depth in chemistry. And I'm not going to be talking about, chemistry that doesn't affect stuff that we'll be talking about later on. Okay, so if this is a review, be happy that you know most of it already and it's not a ton of new material. If you haven't really seen this before, make sure you're understanding what I'm saying. And if you don't, please ask questions. I'll try to clarify. It's easy for me to brush over stuff because a lot of this I've taught many times. So I might not be explaining something in a way, I might be missing out on something that you need. So feel free to ask me if you have questions. I think that's all I have to say before we get started. So we're going to start very basic. First off, why do we talk about chemistry? I kind of already mentioned that. Seems a little strange in a human anatomy and physiology class, but a lot of our physiology, and the anatomy, it's all based on these molecules. We have to know how atoms bond to each other and some of the properties of those in order to figure out, to understand our physiology. So chemistry, you'll see in all of your biology classes, it'll kind of all come back to chemistry in one way or another. So like I said, I'm going to try to make sure everyone's on the same page as far as chemistry goes. Without chemistry, life wouldn't exist. We're just a bunch of atoms that are all well coordinated and working together. Some basic terminology here, atoms, ions, molecules. First off, element. We don't have a periodic table in here, do we? No. So if you look at a periodic table, all of those little squares are all of the elements on Earth. You can't break an element down by any natural means beyond one of its atoms, basically. So it's kind of the simplest form of matter. Can you guys see the screen okay? Do I need to turn the lights out? Don't fall asleep. It won't be that dark. That didn't help. There's 24 elements. So if you look at the periodic table, there are way more than 24 elements. There's only 24 that really play an important biological role. And of those 24, we're going to be focusing heavily on only 6. So that's really nice. We're whittling down the periodic table to 6 elements that make up 99% of our body mass. If you're not familiar with these element symbols already, I'll go through them. CH and O, we're going to see over and over again. Carbon, hydrogen, oxygen. Those are going to be our three of the big ones we'll talk about a lot. Nitrogen is another big one. And then calcium and phosphorus. Calcium and phosphorus are particularly important in our structural makeup, like bones and teeth. So a lot of our structure is calcium and phosphorus. But all of these you'll see again. They'll come up throughout this semester in one form or another. Trace elements are kind of the other elements, not of these 6, that make up the rest of our body. So they're in tiny amounts, but they can be really important physiologically. I'll talk about them, I'll refer to them, but these are kind of the 6 biggies that we'll see many, many times. And I'm probably going to move through this kind of quickly. So because most people have seen some of this before, Feel free to ask me to slow down if you want me to. I don't mind. I just don't want people to get too bored, although it is chemistry. Okay, minerals. Minerals are a specific kind of subset of elements in our body. They are inorganic, doesn't really matter. You don't have to worry about exactly what that means, but they're elements that are taken out of the soil by plants. So plants are what actually make these elements usable for us. We eat the plant and then we get it, or we eat the animal that ate the plant and then we get it. So we don't make these, we get them via ingestion. They make up about 4% of our body mass, and they include a couple that I mentioned already, calcium and phosphorus. So those are 2 minerals. And then a few other elements. Cl is chlorine, Mg is magnesium, K, potassium. That's kind of the only, well, I guess sodium doesn't really make sense either, but I've seen sodium so many times that Na just makes sense to me. But potassium is K, Na is sodium, and S is sulfur. We'll talk a lot about sodium and potassium. If you guys remember from 1101, the sodium potassium pump, that's essentially what allows all of our nerves and muscles to fire and function. So sodium and potassium will come up, magnesium, yeah, all these will come up. Sulfur, I don't know that I really talk about much beyond this, but those other 6 will come back up. A lot of these are important in body structure and then the function of enzymes. Enzymes I'll get into towards the end of this chapter, but they're basically just proteins that help all the chemical reactions in our body work more efficiently. You don't need to know all these numbers, but I think this is a nice graphic to kind of show you what we're made of. Oxygen, carbon, hydrogen. The vast majority of what we're going to be talking about is carbon, hydrogen, oxygen. The others are in smaller amounts. And then down here, we have all the trace elements that most of which I haven't even really mentioned. Okay. Now we're going to break down chemistry into looking at how an atom is structured. So most of you have probably seen these terms before: proton, neutron, electron. I'm going to talk about where they occur, kind of what they do, how they make an atom reactive or non-reactive. Okay, so I am going to use what's called the planetary model of atomic structure. It's sort of a simplified model of what an atom looks like. So like an atom of carbon, 1 unit of carbon. We have this central area, which is the nucleus. And then outside that are these orbitals or energy levels. In the nucleus, you have protons and neutrons. So the 3 subatomic particles are protons, neutrons, electrons. Protons and neutrons are in the nucleus. Protons are positively charged. Neutrons are neutral. They don't have a charge. Electrons are what are found in these energy levels surrounding the nucleus. So these little orbitals. Electrons are negatively charged. I think I said that. Electrons are negative. Protons are positive. The atomic number specifically refers to the number of protons in an atom. So how many protons are there in the nucleus? That's the atomic number. For carbon, there are 6 protons in the nucleus. And then for our purposes, most of the time, it's going to be the same number of electrons. So if there's 6 protons, there's also 6 electrons. And they're found out in these orbitals in the energy shells. Okay, the outermost shell is called the valence shell. I'll talk about that. So you can see there's 2 shells on carbon, right? The second one is the valence shell. That'll come into play when we talk about what carbon is going to bond with. So how many electrons are in this valence shell? will determine how reactive an element is and what it will actually bond with and what it won't bond with. So the valence shell we're going to focus on when I get into the molecular bonding. What else here? Oh yes, the number of electrons that can fit in each shell. This is important. And I'm going to go down here to sodium. It has more shells. So no matter what element you're talking about, this first shell can fit 2 electrons and only 2 electrons. It's tiny. Sodium has a total of 11 electrons. It has to spread them out over these shells. So it's the first shell holds 2. The second shell, sorry, it's hard to line it up perfectly. The second shell holds 8, and the third shell can hold 8. So 2, 8, 8. That's the maximum number of electrons that can fit in each shell. We're not going to go beyond 3 energy shells. We're not going to talk about anything really regarding this structure that goes beyond 3 shells. So sodium has 11 electrons. Its atomic number is 11. It has 11 protons, which means it has 11 electrons. 2 will fit in that first shell. 8 will fit in the second. That's only 10, right? So we still have 1 lonely electron. It has to go into a third energy shell. So you kind of think of it as filling from the inside out. The only weird one is that first energy shell that can only hold 2. The others can hold 8. So you can figure out how many, what we're going for here really, is how many electrons there are in the final energy shell, in the outer valence shell. And I'm going to talk about that on the next slide. Questions about that? It's a general setup of an atom. Okay. So focusing on that outermost shell, the number of electrons in the outermost shell, or the electrons in the outermost shell are referred to as the valence electrons. The number of valence electrons determines how or if an atom will bond to another atom. And the determining factor there really is the fact that all of these atoms want to have a full outer shell. So for most atoms, that's going to be 8 electrons. They want 8 electrons in that outermost shell. It might be the second shell, it might be the third shell, but they want 8. That's the octet rule. Octet meaning like octopus 8. So generally they're going to want 8 in their outermost shell. And they'll do different things to kind of get 8 if they don't have them. So carbon only has 4 in its outermost shell over here. 1, 2, 3, 4, because it only has 6 total electrons. So 2 in that first shell, 4 in the outermost. So it wants to get 4 more. It might share, usually it will share. So it'll share to get 4 more electrons, and then it's happy. Oxygen has 8 total electrons, 6 valence, so 6 in the outermost. So it only needs 2 more. So oxygen is pretty reactive. It'll react with a lot of stuff because it only needs 2 to get to that full valence shell. Questions about that? Hydrogen's a weirdo. Hydrogen is the only element that we're going to talk about that only has 1 electron shell, 1 energy shell, because it only has 1 electron. Hydrogen's super tiny. It has 1 proton, 1 electron. It's very simple. So it doesn't need another shell beyond the first one, right? Because there's still a blank spot there. So it can hold on to, it wants to get 1 more. So hydrogen only needs 1 to fill its valence shell to get to 2. All of the other elements want to get to 8. Hydrogen's the unique one there. Okay, so if we look at the periodic table, I'm going to black out the whole middle. We don't care about it. We don't care about most of the periodic table actually in this class, but we're going to ignore that whole middle part. And from this, you can tell how many valence, well, you can tell how many valence electrons there are, how many total electrons there are. You can tell a lot about an element based on where it is in the periodic table. We're going to talk about the most basic aspects of that. So in this first column, if we start on the left, so like we read from left to right, this first column has one valence electron. These numbers up here, the Roman numerals, this is 1A, 2A, 3A, all the way over to 8. It's just the column number, essentially. If you ignore all of these columns in the middle, you can go 1, 2, 3, 4, etc. You can count over. That's the number of valence electrons in each atom. So if we look at lithium, which is something we won't really talk about, it only has one valence electron, and that's what we're most interested in. Sodium too, we'll talk about sodium. So one valence electron, if we go all the way over to the other side, did that come up? There. This column has 7 valence electrons. That's the Roman numeral 7 here. I know it's super tiny, but like I said, you can just count over. 7 valence electrons. How many more electrons do these elements need to fill up their outermost shell? Just one, right? This is a super reactive column. They only need one electron, so they will react with a lot of different things to get that one electron. Fluorine is very reactive, chlorine as well. Okay, so number of valence electrons, the atomic number. Here you can see the what all of these things mean in each of the squares. The atomic number is above the symbol for the element. So hydrogen has one atomic number of 1, which means it has 1 proton and 1 electron. All the way over here, oxygen, that's an 8. You probably can't see that. It has 8 electrons. So from that, you can figure out how many electrons are in each shell, right? There's 2 in the first one, 6 in the second one. That means oxygen needs 2 more to fill up its valence shell. So I want you to be able to tell me how many total electrons there are and how many valence electrons there are for any of these elements. Really, I'm not going to go beyond here. So potassium and calcium are kind of the lowest elements we're going to talk about. So they're up. Questions about that? Okay, why do we care? Because the setup of the atom, how many valence electrons there are, is going to determine how it bonds to another atom. We need atoms to bond to each other to make anything really. Water, the different tissues, the cells, all of that is because these different elements bond to each other. And that is all because of their valence electrons. And if we go back to the octet rule, we know that all of the elements, the atoms, want a full valence shell. That's what we're going for. That's what they're going for when they make bonds. These are the 4 bond types I'm going to talk about. Hopefully they look kind of familiar. The strongest bond is a covalent bond. And then it gets weaker as we go down the list. Ionic, hydrogen, and then van der Waals forces. I'll talk about what each of these is on the next few slides. First, covalent bonds. When you think covalent, think sharing. Electrons are being shared between 2 atoms in a covalent bond. They're not being totally transferred, they're sharing. And that makes it a really strong bond, because if they stop sharing, they're sharing in order to fill up their valence shell. If they stop sharing, then they don't have a valence shell anymore. So there's a strong desire to keep that sharing relationship going between 2 atoms. If we look at hydrogen, remember hydrogen's a really simple one. How many electrons does hydrogen want in its valence shell? Total. 2. Yeah, it wants 2. It only has 1. Conveniently, 2 hydrogen atoms each have 1 that they can share with each other, right? So if they bond together and stick together, now they have full valence shells, both of them. They both benefit from it. It's like a symbiotic relationship. So yeah, difficult to break. Usually it requires some kind of special protein like an enzyme to break them apart. There's 2 subcategories of covalent bonds, polar and nonpolar. This probably sounds kind of familiar as well, hopefully. I'm going to talk about polar first. It's a little bit easier to explain nonpolar when I've talked about polar first. Okay, so you have a polar covalent bond when you have typically 2 different elements bonding together. So here we have an oxygen and a hydrogen. It's not showing their electrons, so we're not too worried about that. If an oxygen bonds with a hydrogen, the oxygen holds the electrons closer to it. It is greedier, it's selfish. Hydrogen can't hold on to them as strongly. So the electrons are actually shifted a little bit more towards oxygen. That creates a slightly negative charge around oxygen. So that's what this is referring to. Slight negative charge, leaving hydrogen slightly positively charged. Just because the electrons are a little bit further over here and electrons are negative, right? So if the negative charges are closer to oxygen, that creates a slight negative charge on this side of the molecule, leaving this side positive. So this is called polar because you have 2 poles. You have a positive pole and a negative pole. This will come into play with water. It does the same thing, H2O. Oxygen will hold on to those electrons a little bit more closely, and you get a polar covalent bond. If you have 2 elements that are the same, 2 carbons, for instance, one isn't pulling more strongly on the electrons than another one because they're the same. They're exactly the same. So that's going to be non-polar. That means they don't have any charge. There's no charge associated with them. They're sharing the electrons totally equally. So equal sharing of electrons in a nonpolar, unequal sharing of electrons in a polar covalent bond. And that polar covalent bond will come up again when we talk about hydrogen bonds in a couple slides. Questions about that? That's kind of critical, understanding a polar covalent bond in particular. All right, ionic bonds. We're not sharing anymore, no more sharing of electrons. We're totally transferring an electron from one element, from one atom to another. So the atom that donates that electron it becomes positively charged and it's called a cation. If you get rid of a negative charge, that element then becomes more positive, right? So it's positively charged, it's a cation. On the other side of that, you have to have an element that's going to accept that electron. That acceptor becomes the anion. It's taking on more negative charge in the form of that electron. So it is negatively charged and it's the anion. This process in general is called ionization. And sodium chloride is a really easy, great example of an ionic bond. What is sodium chloride? Does anyone know? Salt, table salt, right? So if you use salt on anything, you're using sodium chloride. So you have a sodium atom, you have a chloride atom, or yeah, sodium, chlorine. These will readily bond with each other. So if we look at the valence shells of each of these, sodium has one little electron in its outermost shell. Chlorine has 7. That lines up pretty well, right? So is it easier to get rid of 1 electron or to gain 7? Just get rid of 1, right? Get rid of 1 thing rather than trying to get 7 things. So sodium is going to get rid of its 1 valence electron, give it to chlorine. So now chlorine will have 8. That outer energy level is then, it just disappears without that 1 electron taking up space on it. So its second energy level is now its valence shell, and it's full. It has 8 in it. So sodium's happy, chlorine's happy. That's why this bond so readily happens. Sodium becomes the cation, positively charged. Chlorine becomes chloride, the negative ion. It's negatively charged. The anion, yeah, anion.
So the one that gives it becomes positive.
Yes, the one that gives it away becomes positive because it's getting rid of a negative charge. So it's getting more positive. And these are, ionic bonds are pretty strong, but they are easily broken by water. You know, it's easy to dissolve salt in water, right? You're breaking that bond when you dissolve salt in water. And that's all I'm going to say about ionic bonds for right now. Hydrogen bonds. This is, like I said, going to go back to that polar covalent bond. So we have to understand the polar covalent bond before we can really understand a hydrogen bond. A hydrogen bond always involves hydrogen, so that's an easy first step to understanding this. It's a fairly weak attraction, and it happens between molecules that are made of polar covalent bonds. So if we look at water, water is a really good example. We have an oxygen and 2 hydrogens, H2O, right? That's our water. And I mentioned that water is polar covalent, it has polar covalent bonds. So oxygen is really greedy for electrons. It holds the electrons closer to it, but it's still sharing. These are all sharing. So oxygen is sharing an electron with each hydrogen. So oxygen, because it holds onto those electrons more closely, is slightly negative. And then the other side of the molecule is slightly positive by default. So that's a polar covalent setup. So we have these negative and positive ends of a water molecule. Opposites attract. So this negative end of the water molecule here is going to be attracted to the positive side of another water molecule. So we still have the positive and negative set up down here with another water molecule. So this positive hydrogen is going to be attracted to this negative oxygen, and that'll create a kind of weak bond. That's why water molecules are attracted to each other. We'll talk about properties of water in a few minutes. But it'll pretty readily break and then reform kind of over and over. So they're not super strong, but they do hold water molecules together. You have to have a molecule that has this polar covalent bonding in order to have hydrogen bonding between the molecules, because you have to have a positive and a negative. If it's non-polar, then there's no negative positive attraction to be had. I'll mostly talk about hydrogen bonds when we're talking about water, but they also come up, they occur in DNA and then proteins as well. So they're found elsewhere. I just won't talk about them. I'll mostly talk about them with water because it makes a lot more sense. It's a little bit simpler to talk about. Yeah, okay. The final bond, I won't spend much time on and it won't really come up again. This is called van der Waals forces. These are really weak and very brief. So they're constantly changing. They're not even more so than hydrogen bonds. They are important in protein folding. So we have hydrogen bonds in proteins. We also have these van der Waals forces, which create the shape of the protein, and the shape of a protein matters in its functionality. So what these are, if we look at a very simple atom, how I've described atoms is this nucleus, right, surrounded by an electron cloud. And every picture I've shown you so far, the electrons are kind of evenly spread out around that, right? That's not really how atoms are set up. These electrons are constantly spinning around the nucleus. And sometimes they'll all be on, say, the right side of the nucleus, or they might all be on the left side of the nucleus. They're constantly moving around. So if all of the electrons in this atom are kind of off to the right at one point in their movements, that atom will be attracted to the positive end of another atom. So that's why it's so brief. These electrons get into this position and then instantaneously almost move to another position. So then this bond will break apart. But it's all due to the motion of the electrons around the nucleus. They're just constantly shifting around. And wherever that negative charge is, it'll be attracted to the positive side of another atom. Good? All right, into water. So that's going to bring us, we talk about water in 1101 quite a bit. This will be a very shortened version of that. Some of the characteristics of water. Water is really important. We are, depending on your age and your gender, you're made up of anywhere between 2/3 and 3/4 water. So we have a lot of water in our body. All of the fluids in our body, the main base of those is water. So understanding the properties of water, kind of critical to eventually understanding, say, blood, and how it flows and the different elements of blood. We're not talking about blood in AMP1, but when you get into AMP2, you'll talk about the circulatory system. So the properties of water that are amazing from our point of view, from a human anatomy point of view, is the fact that it is a universal solvent, which just means it dissolves almost everything, not almost everything. It dissolves a lot of things very effectively. So if you've ever made like a lasagna and you have it in that, like the baking dish, and then you leave it for too long, and you can't physically even scrape out that cheese sometimes, right? If you put it in the sink and you put water in it, it almost miraculously just dissolves all of that hardened cheese and sauce and whatever else is in there. So it dissolves things very effectively, and in our bodies, that's really important. Water is going to carry a lot of the nutrients, a lot of the molecules around our body, and it has to dissolve them a lot of times in order to do that. Cohesion and adhesion. Hopefully those two words look very familiar. Does anyone remember what cohesion is? These are attraction of water molecules to something else. Water to water is cohesion. Yeah, so two water molecules being attracted to each other, that's cohesion. They'll stick together. That's those hydrogen bonds that I talked about. Does anyone remember what adhesion is? Water being attracted to, yeah, polar molecules. So anything else that's polar, not water, but anything else. So glass, wood, leaves, water is attracted to all of these other polar substances. It has to be polar because, again, it's the hydrogen bonds that are keeping those molecules stuck together. So cohesion, attraction of water to itself. Adhesion is the attraction of water to other polar molecules. And then thermal stability. I don't know if we really touch on this. I guess we do somewhat in 1101, but this is really important from a human point of view because we are made up of up to 3/4 water, and it's really hard to change the temperature of water. It doesn't change very readily. That means our internal temperature stays very stable. So thermal stability is great for our homeostasis, and we need it, and water really helps contribute to that. Those are the 4 main properties of water. This video I'm going to show you goes into a little bit of detail about those. Do you guys know Crash Course, that series on YouTube? Yeah, so this is a Crash Course video. If you're not familiar with Crash Course, they have a whole AMP playlist. So they have a human anatomy and physiology playlist on YouTube. He goes into more detail in some places than I do, or vice versa. I might go into more detail than he does, but it's a really nice review. They're like 10 or 12-minute videos that will review major systems of the body. So if you need a little bit more explanation, I definitely recommend Crash Course. He talks kind of fast sometimes, although so do I. So, but you can always pause him and listen to him at your own speed.
Here at Crash Course HQ, we like to start out each day with a nice, healthy dose of water in all its three forms. It is the only substance on all of our planet Earth that occurs naturally in solid, liquid, and gas forms. And to celebrate this magical bond between two hydrogen atoms and one oxygen atom, here today we are going to be celebrating the wonderful life-sustaining properties of water. But we're going to do it slightly more clothed. Much better. We left off here at the biology crash course. We're talking about life and the rather important fact that all life as we know it is dependent upon there being water around. Scientists and astronomers are always looking out into the universe, trying to figure out whether there is life elsewhere, because that is kind of the most important question that we have right now. They're always getting really excited when they find water someplace, particularly liquid water. And this is one reason why I and so many other people geeked out so hard last December when Mars' 7-year-old rover Opportunity found a 20-inch long vein of gypsum that was almost certainly deposited by long-term liquid water on the surface of Mars. And this was probably billions of years ago. And so it's going to be hard to tell whether or not the water that was there resulted in some life. But maybe we can figure that out. And that would be really exciting. But why? Why do we think that water is necessary for life? Why does water on other planets get us so friggin' excited? So let's start out by investigating some of the amazing properties of water. In order to do that, we're going to have to start out with this. The world's most popular molecule, or at least the world's most memorized molecule. We all know about it. Good old H2O. 2 hydrogens, 1 oxygen. The hydrogens each sharing an electron with oxygen in what we call a covalent bond. So as you can see, I've drawn my water molecule in a particular way. This is actually the way that it appears. It is V-shaped. Because this big old oxygen atom is a little bit more greedy for electrons, it has a slight negative charge, whereas this area here with the hydrogen atom has a slight positive charge. Thanks to this polarity, all water molecules are attracted to one another. So much so that they actually stick together, and these are called hydrogen bonds. And we talked about them last time. But essentially what happens is that the positive pole around those hydrogen atoms bonds to the negative pole around the oxygen atoms of a different water molecule. And so it's a weak bond. But look, they're bonding. Seriously, I cannot overstate the importance of this hydrogen bond. So when your teacher asks you, what's important about water? Start out with the hydrogen bonds and you should put it in all caps and maybe some sparkles around it. One of the cool properties that results from these hydrogen bonds is a high cohesion for water, which results in high surface tension. Cohesion is the attraction between two like things, like attraction between one molecule of water and another molecule of water. Water has the highest cohesion of any non-metallic liquid, and you can see this if you put some water on some wax paper or some Teflon, or something where the water beads up like this. Some leaves of plants do it really well. It's quite cool. Since water adheres weakly to the wax paper or to the plant, but strongly to itself, the water molecules are holding those droplets together in a configuration that creates the least amount of surface area. This is high surface tension that allows some bugs, and even I think one lizard, and also one Jesus, to be able to walk on water. The cohesive force of water does limits, of course. There are other substances that water quite likes to stick to. Take glass, for example. This is called adhesion, and the water is spreading out here instead of beating up because the adhesive forces between the water and the glass are stronger than the cohesive forces of the individual water molecules in the bead of water. Adhesion is attraction between two different substances, so in this case, the water molecules and glass molecules. These properties lead to one of my favorite things about water, the fact that it can defy gravity. That really cool thing that just happened is called capillary action. And explaining it can be easily done with what we now know about cohesion and adhesion. Thanks to adhesion, the water molecules are attracted to the molecules in the straw. But as the water molecules adhere to the straw, other molecules are drawn in by cohesion, following those fellow water molecules. Thank you, cohesion. The surface tension created here causes the water to climb up the straw. And it will continue to climb until eventually gravity pulling down the weight of the water and the straw overpowers the surface tension. The fact that water is a polar molecule also makes it really good at dissolving things, which we call it's a good solvent. Scratch that. Water isn't a good solvent. It's an amazing solvent. There are more substances that can be dissolved in water than in any other liquid on Earth. And yes, that includes the strongest acid that we have ever created. The substances that dissolve in water, sugar or salt, being ones that we're familiar with, are called hydrophilic. And they are hydrophilic because they are polar, and their polarity is stronger than the cohesive forces of the water. So when you get one of these polar substances in water, it's strong enough that it breaks all the little cohesive forces, all those little hydrogen bonds, and instead of hydrogen bonding to each other, the water will hydrogen bond around these polar substances. Table salt is ionic, and right now it's being separated into ions as poles of our water molecules interact with it. But what happens when there is a molecule that cannot break the cohesive forces of water? It can't penetrate and come into it. Basically, what happens when that substance can't overcome the strong cohesive forces of water? It can't get inside of the water. That's when we get what we call a hydrophobic substance, or something that is fearful of water. These molecules lack charged poles. They are non-polar, and they're not dissolving in water because essentially they're being pushed out of the water by water's cohesive forces. Water, we may call it the universal solvent, but that does not mean that it dissolves everything. There have been a lot of eccentric scientists throughout history, but all this talk about water got me thinking about perhaps the most eccentric of the eccentrics, a man named Henry Cavendish. He communicated with his female servants only via notes and added a staircase to the back of his house to avoid contact with his housekeeper. Some believe he may have suffered from a form of autism, but just about everyone will admit that he was a scientific genius. He's best remembered as the first person to recognize hydrogen gas as a distinct substance and to determine the composition of water. In the 1700s, most people thought that water itself was an element. But Cavendish observed that hydrogen, which he called inflammable air, reacted with oxygen, known then by the awesome name dephlogisticated air, to form water. Cavendish didn't totally understand what he discovered here, in part because he didn't believe in chemical compounds. He explained his experiments with hydrogen in terms of a fire-like element called phlogiston. Nevertheless, his experiments were groundbreaking, like his work in determining the specific gravity, basically the comparative density of hydrogen and other gases with reference to common air. It's especially impressive when you consider the crude instruments he was working with. This, for example, is what he made his hydrogen gas with. He went on not only to establish an accurate composition of the atmosphere, but also discovered the density of the Earth. Not bad for a guy who was so painfully shy that the only existing portrait of him was sketched without his knowledge. But for all of his decades of experiments, Cavendish only published about 20 papers. In the years after his death, researchers figured out that Cavendish had actually pre-discovered Richter's law, Ohm's law, Coulomb's law, several other laws. That's a lot of freaking laws. And if he had gotten credit for them all, we would have had to deal with like Cavendish's 8th law and Cavendish's 4th law. So I, for one, am glad that he didn't actually get credit. We're going to do some pretty amazing science right now. You guys are not going to believe this. Okay, ready? It floats. Yeah, I know you're not surprised by this, but you should be, because everything else, when it's solid, is much more dense than when it's liquid, just like gases are much less dense than liquids are. But that simple characteristic of water, that its solid form floats, is one of the reasons why life on this planet, as we know it, is possible. And why is it that solid water is less dense than liquid water, while everything else is the exact opposite of that? Well, you can thank your hydrogen bonds once again. So around 32 degrees Fahrenheit, or 0 degrees Celsius, if you're a scientist or from a part of the world where things make sense, water molecules start to solidify, and the hydrogen bonds in those water molecules form crystalline structures that space molecules apart more evenly, in turn making frozen water less dense than its liquid form. So in almost every circumstance, floating water ice is a really good thing. If ice were denser than water, it would freeze and then sink, and then freeze and then sink, and then freeze and then sink. So just trust me on this one. You don't want to live on a world where ice sinks. Not only would it totally wreak havoc on aquatic ecosystems, which are basically how life formed on the Earth in the first place, it would also, all of the ice in the North Pole would sink, and then all of the water everywhere else would rise, and we wouldn't have any land. That would be annoying. There's one more amazing property of water that I'm forgetting. Why is it so hot in here? Heat capacity. Yes, water has a very high heat capacity, and probably that means nothing to you, but basically it means that water is really good at holding on to heat, which is why we like to put hot water bottles in our bed and cuddle with them when we're lonely. But aside from artificially warming your bed, it's also very important that it's hard to heat up and cool down the oceans significantly. They become giant heat sinks that regulate the temperature and the climate of our planet, which is why, for example, it's so much nicer in Los Angeles, where the ocean is constantly keeping the temperature the same, than it is in, say, Nebraska. On a smaller scale, we can see water's high heat capacity really easily and visually by putting a pot with no water in it on a stove and seeing how badly that goes. But then you put a little bit of water in it, and it takes forever to freaking boil. Oh, and if you haven't already noticed this, when water evaporates from your skin, it cools you down. Now, that's the principle behind sweating, which is an extremely effective, though somewhat embarrassing part of life. But this is an example of another incredibly cool thing about water. When my body gets hot and it sweats, that heat excites some of the water molecules on my skin to the point where they break those hydrogen bonds and they evaporate away. And when they escape, they take that heat energy with them, leaving me cooler. Lovely. Well, this was an exercise, though. I don't know why I'm sweating so much. It could be the spray bottle that I keep spraying myself with, or maybe it's just because this is such a high-stress enterprise trying to teach you people things. Anyway.
So we'll talk about sweating in the integumentary system. So that'll come back up. That's it for now. Don't forget to turn in, no labs this week, but turn in your